Hello, class. My name is Marcos Cardenas, and today I'm going to be talking about high voltage direct current. First things first, what is high voltage direct current, or HVDC? What I found out was that it's technology that transmits electricity over long distances by overhead transmission lines. These lines are held between two power stations, and the system usually includes inverters. These inverters are necessary for the power distributed to be used in our current system. And as you can see in the picture below, you can see two different types of transmission poles, wires, or how it's set up. So the long skinny ones are usually DC, and then the wider ones or crossed ones are AC. The origins of high voltage direct current, the concept of which power to use was discussed by three intelligent and innovative men known as Tesla, Edison, and Westinghouse. Edison was the lead man that led the direct current war, meaning that he was pushing for the grid to run on DC. Thomas Edison and Westinghouse had other plans and other ideas. So, process of electrical power. Delivering renewable energy with HVDC. So what I'm going to tell you right here is just how it works. So the generation to the transmission line, the distribution basically, and then it being inverted, and then the distribution to the consumer, meaning us, or like people, buildings, stuff like that. So first it starts off with the generation, which is wind power. Well, this example is wind power. You can have hydroelectric. You can have different types of generation. And what it does is it converts AC power to DC power. The energy is transmitted on the transmission line, meaning that once it hits the AC transmission line is converted to DC, then the HVDC transmission lines carry it over long distances, usually with minimal loss and stuff like that. Then it meets another inverter, so another inverter station, and converts it back to AC, and the energy is received and it's converted into AC and connects with the existing transmission system. And the existing transmission system is an AC, so our grid is AC powered. So then in the next section, AC transmission lines, and then it's distribution lines, meaning the regular poles you see on the street, and then the ones that connect to our houses and our buildings and businesses. And I got this all from Clean Line Energy Partners Greenbelt Express. Forms of electric generation. We talked about wind power, which is windmills, we also have hydroelectric generation, and we also have solar power. Hydroelectric generation, prime example is dams. It's falling water that causes the turbines in the electric system to generate electricity. Wind power is windmills that have most common equipment. Have been the most common equipment to gather wind power. The wind causes the turbines to rotate, causing the copper armature and the generator to generate electricity. And solar power is using infinite heat from the sun. Photovoltaic cells utilize the energy of the sunlight to generate electricity. So like the solar panels and all that, each square or each circle, whatever it's made out of, is a photovoltaic cell. And then this form of generation is becoming more useful nowadays. So there's a lot of businesses and a lot of homes, even just homes, that are using solar power. Hydroelectric generators in the U.S., three different types. There's pumped, impounded, and diversion. Pumped stores energy by pumping water uphill to a reservoir at higher elevation from a second reservoir at lower elevation. Impounded means it uses a dam to store river water in a reservoir. Water released from the reservoir flows through a turbine, spinning it, and which in turn activates a generator to produce electricity. And then diversion is a runoff river. Facility channels a portion of a river through a canal or a penstick. So the first one is going to be the pump. So you get a lower elevation. The bottom left one's going to be lower elevation to higher elevation. And it's just going to pump the water up. The top picture up here is going to be the dam and how it's storing energy at the cross section. And then the intake, meaning that the water goes through one way, the energy goes through one way, and it comes out the other. wind power generators turns wind energy into electricity using aerodynamic force. Two types of turbines usually are horizontal or vertical axis turbines. The size of the turbines can range from being very small and home viable to extremely big that needs an abundance of room. So, for example, there are sometimes windmill farms that are basically just for wind generation or wind electrical generation. And then you can also have those small ones that are behind those farms and stuff like that. Last form of generation is solar power. And according to Interesting Engineering, a solar power plant is any type of facility that converts sunlight either directly, like photovoltaics, or indirectly, like solar thermal plants, into electricity. And there's usually two different types of systems. There's standalone, and there's grid type systems. And a picture next to it, it's going to explain how it works. So a PV system can be grid connected or standalone. Grid connected is usually directed connected to utility or the bi-modal PV system. And with the bi-modal is the storage system. And the directed connected to utility doesn't have a storage system. And then the standalone PV system, it can be two different types. So that it can be with battery or without battery, hybrid or a hybrid PV system, and then the without battery just direct coupled system. With batteries, a DC self-regulating, and then also an AC system with charge controller for battery and load. For the hybrid PV system, with wind turbines, hydro turbines, with diesel generators, with fuel cell or other sources that power it, basically, or what it powers. And then some statistical benefits of DC, and I got this all from the National HVDC Center. And then it says HVDC offers a range of technical, environmental, and economic advantages over HVAC. Over long distances, HVDC is more efficient and has lower electrical loss compared to AC. DC power is usually the power that is consumed in our society. Society's electric motor, heating element, and electronics. So those are the main three that DC power is usually used in. DC converters are becoming more and more efficient and inexpensive. The invention of the vanadium flow battery further simplifies the DC voltage conversion. In DC systems, the charging current is low. Therefore, the length of the transmission line is longer, meaning that it can travel longer distances. HVDC are also environmental friendly, and the plants are able to be the DC power plants are able to be used more efficiently as well. Some cons of the DC power. The most disadvantageous reason behind using DC power is that our electric power system is AC power based, so our grid is AC power based, and that means that we have to include inverters in our systems to convert it from DC to AC and then convert it back, so vice versa. So we have to keep converting it when we want to distribute our power or transfer our power from the north to the south or from the east to the west, stuff like that. Electric power can travel in the form of DC, but it's not really useful for small electronic components. Also, there is a limit to the DC switches and circuit breakers, and one main thing is that it's very costly, so it's extremely costly. Converting DC electrical power to electrical appliances that use low voltage is hard to achieve, meaning that the household appliances, air conditioner, computer, dryer, freezers, like the fridge, the washer, all that type of stuff is all electrically charged and powered, So I mean, there's not going to be that much power. DC is usually high voltage, so that's why we use AC. Environmental issues of DC is the audible noise and the visual impact, so it's loud, and electromagnetic compatibility as well. So it has a field. And then going back into the cost and talking a little bit about that, as we can see, the images. First off, the images from research done by Siemens graphically explains the comparison of AC and DC costs, with the variable being transmission distance, as you can see down below of the graph. It clearly shows the benefit of DC over longer travel as well. And then if you notice, the break-even distance is set to be 500 to 800 kilometers. The cost graph displayed also does not have the cost of the fees and rates. So there's other fees and rates that also affect the cost. And if we look at the diagram, we can see that the total cost for DC in the long term or in the long run is cheaper. So if it goes further distance, that means that DC is obviously more affordable than AC, because AC, as the distance increases, the cost increases dramatically. So it's almost as if it's increasing by the double. What else can I say about the AC losses as well? There's a lot more AC loss than there is DC losses, as you can see right there in the middle, highlighted in blue. AC loss is bigger than DC loss. That's pretty much it. And then here below are helpful links for more understanding of DC high voltage direct current. They also explain a little bit more about how it compares to HVAC, so the high voltage AC power, and they go in depth about why DC is better or why AC is better. So thank you guys for paying attention. I hope you guys learned a little bit something. Thank you and have a good day.